Good morning, everyone. Thank you for the introduction, Maurice. My talk was tailored a bit due to the directive from Jonathan. And during our recent hardware porting workshop that we had in South Africa, we also had a lot of students there. Got a lot of questions about how do you end up with this stuff? Where do you start? Why do you do this stuff? Why do you use FPGA, these FPGA things when there's CPUs? Why do you want to do direct sampling? So that sort of guided it or changed the talk that I was giving, but let's go. So I'm going to give an outline, where do we start with everything, the sort of requirements, the wish list. So this is going to build on what Adam said. Derivation of that, mapping to technologies, direct sampling, enabling technologies and new technologies. So where do we start when we're building a radio astronomy telescope? It's normally with some science case. We want to observe something. There's some specific patch of the sky we want to look at. We want to look at a pulsar. We want to image something. We want to time a pulsar. So there's a specific case that we want to observe. And that is the thing that actually drives us to decide, okay, what are we going to build here? Are we going to, what type of technology are we going to use? And what are we trying to do? This gets then into high-level specifications so that we can say, okay, so we've got this wish listing that we just said that we want to do all the stuff. We want to be everything for everybody, and we want to keep everybody happy, and we want to do it great. We're going to do it without costing anything, and it's going to be done in no time. And then we turn it into specifications, and then we do some sanity checks and realize, this will be nice to do this, but it's going to cost us pretty much our country's budget to do that, and it's going to take us the rest of our lives. And then we have to push back and say, listen, guys, we need to rethink this, and we can do this realistically, and we can do that. And then again, we get some agreement. Agreement is important because we need to decide on what is good enough. As we know, your good and my good is not always the same thing, so we need to decide when have we achieved the pass-fail criteria, what is good enough. So this is a system diagram, a so-called V diagram, and it's actually quite a nice way to think about the progression of a project. When I started as an engineer, I was told that a project is defined in 5 stages. The first stage is enthusiasm. The second stage is disillusionment. Third stage is search for the guilty. The fourth stage is punish the innocent. And then the fifth stage is praise and rewards for the non-participants. Okay. That was a very cynical view of engineering project, but there is some truth in that. So now we have got the system specification, and we need to derive from these specifications. We need to derive more details on what is the actual stuff that we're going to do. How are we going to map this to hardware? What technology are we going to use? Are we going to do this in software or in firmware? So these are the things that drives it. So when you start off, there is obviously a lot of enthusiasm over here. We're going to build this great thing. It's going to be awesome. And then we start getting to the requirements and the architecture and detailed design. And then it's like, oh, but this data sheet has this caveat, and you didn't tell me about this. And then sort of like the project gets to this sort of plateau where things like move along, and you test stuff, and then there's like, okay, this is a problem and that's a problem, and then finally you normally reach this part over here where they've got something, it's working in the lab, and now we're all ready to go to site, and then you start doing integration and testing. So your thing works. I mean, I tested my thing. I've got my scope hooked up, and I've got my signal generators, and my stuff works fine. My stuff works, right? Unfortunately, you start integrating, and then there's all sorts of things that come out of the woodwork. And as you can see here, you're like, the pace is nice, you're going downhill, and now you're going uphill again. And then you've got your stuff, and then somebody says, like, right, before we can go to site, there's a thing called an RFI permit that you need for your equipment. And I'm like, RFI permit, what's this? And it's like, no, we need to put this box of yours in this metal chamber, we're going to do a quick test, and then you can go. And it's like, you stand there, and then the guy starts making this sort of funny whistle sound, and he looks at the thing, and then it's like, no, it's like, sorry, this is not working. Back to the drawing board. You make some changes, you do some testing, and now you think, okay, right, you've got your RFI certificate, and everything should be working now, and then you're off to site with your thing. Then you've like get to site, and you get reported. Suddenly, there's commissioning scientists appearing at your desk, and they're asking you this question, like, we see these funny things happening, and then some of this happens, and there's like a little bell that goes on. It's like, I remember there was this irritating thing about my design didn't meet time enclosure. And at that time, I didn't have time to look at time enclosure issues. And I said I would look at it later, and now it seems it's later. But anyways, you figure that out, and then finally you're at the point where where your thing works. So to quickly go through this in the high-level design. So once we have our specifications, we start drawing out sort of block diagrams like this, and we say that okay, we need to obviously acquire the signal from some antenna. We have to turn the electromagnetic wave into some bits, and then we've got lots of processing happening here for beamforming, correlation, to attain the science goals for the imaging. And then we start mapping it to actual technology details, like the scarab that Adam showed. It was just the mapping of the input and output interface that was determined, and it was put in a block diagram. You start doing your hardware design, schematics, and you also do your firmware design. So you get your CASPER tools going, and it's just a one-click. So that's the easy part. It's just a one-click thing. And then if you're lucky, you end up with something that looks like this. That's our digitizer and the CASPER, the Scarab processing board that you will see now. And in the end, we want to go to operational telescope. So we want to go from some block diagram that we had. It's like, this is like what we should be doing, so more or less. And this is what it actually ends up with. And then you've got your dish and your digitizers and your receivers. And it goes over fiber, and you've got all your scarabs in the rack in the processing building. And you are, everything is integrated, everything is talking to each other, and we are doing science. And the praise and the rewards, well, you get some, and then you also hear of people that get a Nobel Prize somewhere that you haven't heard, and they did it with your instrument, but that's also good. So direct sampling. We are we're here for digital signal processing. So somehow we need to take the EM signal that's coming from the sky, we want to couple it onto our receiver, and then we want to turn it into bits so that we can start doing digital processing on that. Typically this is quite demanding, especially when you want to acquire large bandwidths. But fortunately, guys like Xilinx have made some great strides, and ADC vendors that are doing multi-gigasample per second ADCs have produced some wonderful ADCs. We've got FPGA with high-speed I/O links so that we can interface to these high-speed ADCs. And it doesn't help that we can acquire all these ADC samples, but now what we do with them, we need to ship them off to some other processing, and that's where the switching infrastructure that we use, the 10 gig and the 40 gig Ethernet comes into play. And then we need to have boards like the Scarab that can actually ingest all this data and then do the DSP required, the PFD and the FFTs. So another reason why we want to do direct sampling is we want to turn the EM signal as quickly into bits as we can. We don't want to add more analog stages to the receive signal that we've acquired, because it's typically hard to manage environmental effects. Temperature changes, RFI that's on site couples into your analog signal and distorts it. When you're doing analog down conversion, you also get a thing called intermodulation products, which is a really painful thing. And that can contaminate frequencies that you're looking at. So if you're doing spectral imaging and you're interested, like in Mercat's case, in the hydrogen atoms resonant frequency at 1420 megahertz, it would be most unfortunate if you get RFI or intermodulation products ending up in the bin that is on that frequency that you're trying to observe. So we want to, for interferometer like Mercat is, we want gain and phase stability is a pretty important metric. We rely heavy on having a very stable gain and phase response. And once you can always back out stuff if it's well characterized. If it stays stable, then you can always back out the effects later. If it's changing all the time, that gets very hard to do. Dynamic range. Why do we need dynamic range? So typically we want to look at very small signals, and unfortunately there's also RFI like GPS satellites, GSM, Wi-Fi, Bluetooth, TV, and then we've also have, unfortunately, one of the busiest air routes in Africa passing over our site, and there's airplane transponders that also cause problems from time to time. So even though we are at a very pristine site, there is still RFI, where there's RFI, you cannot get rid of that. And a student asked me, okay, I understand this, but it still doesn't make sense to me. And I said to him, imagine yourself standing in a dark cave and you're looking at a small candlelight, and then I come with like a huge spotlight shining into your eyes. That is sort of the effect of RFI. And strong signals can also cause your ADCs to saturate, and you can get compression of your signal, which also add distortion. Direct sampling comes at a cost, though. You get nothing for nothing and very little for a dime. So you typically have to have a very good anti-aliasing filter that has got a flat passband or a linear slope response, low ripple, large out-of-band suppression. You don't want to have adjacent frequencies leaking into your passband, which is basically the same effect as the intermods. And you want a stable filter response over frequency. Now, all these things sound great, but building something like this is quite tricky, and it's a very specialized job. In the case of Meerkat, that requires a large bandwidth. We're acquiring 770 megahertz in our passband. Another thing that is also important that gets overlooked when you're using ADCs is you need to have an extremely low sample clock, so low phase noise, spectrally pure and stable. And you typically also need a very narrow clock filter to filter out any clock harmonics that your clock source adds. So mapping to the technology. So we set requirements and specifications drive our wish list. So for direct sampling, we typically want to know what is the highest RF frequency that we want to sample. So knowing what your highest frequency is determines your Nyquist frequencies, but also the bandwidth that you want to acquire. So in our case, we want to make sure that our bandwidth falls within a Nyquist zone. And the sampling rate gets determined from that. And then the dynamic range. So I just talked about the dynamic range, the amount of ADC bits that we would require to have linearity in our signal and without distorting and compressing. And then another thing that's important is it's great to acquire many gigasamples per second with many bits, but that requires that you need to ship it out and shuttle it out, and that means that your links between processing nodes will obviously have to be able to handle the data rates. And then the DSP resources required to process that data. So it's typically finding the best fit, how we get to the operational, to keep the operational cost down. How do we scale? It might be the solution that we have might be a good solution if we're doing a few antennas. If we start doing 64 or 128 or more than that, then scaling becomes a problem. So another thing that trade-off is wastage. Sometimes you have to trade off whether I'm going to make it less optimal, but it's going to cost me cheaper, but I can accept the wastage. That's why so it's a trade-off there. Power consumption, as I said, is an important thing. We have a lot of these things stacking up. Your electricity bill quickly becomes a pretty big operating expense. And then the RFI environment. Where does this thing need to operate in? If it's in an air-conditioned shielded room somewhere, then you can get away with more. If you like digitizer out on the antenna, the environment, the temperature, the dust, the rain, and then obviously the self-generated RFI, the RFI that your piece of equipment is generating, especially when you're a meter away from a very sensitive receiver, is quite problematic. So the thing that we like about CASPER is that we can have reusable hardware, we can have reusable firmware and software and command and control stuff that was talked about yesterday that helps us to achieve our goals quicker. We've got plenty of roach boards and scatter boards and snap boards, and the D engine that we did for the digitizer was a very RFI. Well, the attention to RFI was quite a lot there. There's a low RFI board. So why FPGAs? Why not CPUs? Well, it's the logical choice. And as my lecturer said to me, how hard can it be? It's just zeros and ones. So difference between there's been some talk about this, but for FPGAs for us works, especially at sampling, you want to do stuff in real time. We want to acquire the samples are coming out of the ADC at the clock rate. We cannot tell it, okay, listen, hang on, I'm just busy here. You have to ingest the samples. It has to get packed. So we need deterministic processing, and we need to timestamp the samples so that we know after we lining up all the antennas. We need to know when did this data happen. For stuff like pulsar events, we actually want to tie that to some actual UTC time to figure out when this event happened and tie that up. So for that stuff, you need deterministic latencies. FPGA is also very good. It's got a good match between its I/O, its memory, and its processing bandwidths, and you can tailor it. It's also power efficient. And you can as I said, the operational budget gets affected by that. The key features that we like about FPGAs is its multi-gigabit transceivers for the interface, as I said, high-speed IOs, DSP, DRAMs it's well suited for FIR filters and FFTs, and then we can also have hard and soft CPUs in terms of Zinc and microblaze. Yeah, so I'm just going to skip over that. So we've got some software packages that you can use that was talked about yesterday to make your interfacing to your firmware easier. And then I just want to close off and say, why do we carry on? Why do we do all these things? Why do we constantly push the boundaries? So we're looking at having talks about 100 gig Ethernet. We're looking at greater than 10 gigabits per second ADCs with larger analog bandwidths. We're looking at super logic region FPGAs. That's got the HBM, the onboard memory on the FPGA, and the co-processing. Why do I always pushing the bandwidth? And you can have equations and stuff, but in the end, we want to see more things. We want to see more things at the same time. We want to have sharper and better images. We don't want to see Lego men. We actually want to see people's faces, and we want to do more observations, get a better quality of observations, and measure better. And to me, the thing that sort of makes it very visualizes it very well for me is just to look at this. So this was an image taken of a patch of the sky with Cat7, which was our prototype antennas. It was a 7-antenna array. It had RF over fiber link, so the digitalization was done far away from the antenna. 400 megahertz of bandwidth, and it was 8-bit ADC. So there we come. So that's the same image with Meerkat with 4 antennas, direct sampling, 770 megahertz of bandwidth, and a 10-bit ADC. And this is with 16 antennas. So that's the same patch of sky. So more is better. And that's it.
Commercially available ASICs, spectrometer ASICs, and the FPGAs together?
Not really, no.
In the future, that's going to be a strong contender. They have a Swedish company, Omnisys, that has a ASIC spectrometer, and also Pacific Microchip, which is evaluated their new spectrometer. And I could see how the FPGA and the spectrometer could work in sync, where you can move a lot of the heavy processing that's so power hungry into the ASIC, because you're always doing a poly-based filtering.
Yeah. So Jason would probably be the guy to answer that. But we have done some studies to look at trade-offs of processing.
I think in some cases that's probably a good idea. It might benefit you, but in facility instruments like Meerkat, where you have to do lots of different things and you actually don't know what you're going to have to do in the future, you need to be able to change things. And so we've actually spent this past year redoing 2 of our filter banks that we had done and tested and met all our requirements, but after they started using them, the users say, oh, can't we tweak this little thing here and change this thing here? And then you end up changing it completely.
We do have a tool flow that makes ASICs. You can take one of your simulated design and make an ASIC. We've done that a few times for spaceflight, but it's super inflexible. That Omnisys stuff, you can't really change anything. It's very difficult to use.
Okay, one more question, and then we'll break off for coffee. Okay, thank you very much, Henno, and thanks all.